Assalamu alaikum. Welcome to lecture 19 of data mining. So in the last lecture, we had discussed the K-means clustering algorithm. The K-means clustering algorithm is a partitional clustering algorithm that takes K, which is the number of clusters or desired number of clusters as input. And we discussed the algorithm as well as some of its properties. So we will wrap K-means up today and then move on to some other variants of partitional algorithms. And then after that, we will start with hierarchical clustering algorithms. So that is basically the agenda for today. We will be primarily discussing hierarchical clustering after wrapping up the K-means clustering algorithm. So let's just wrap up the K-means clustering algorithm. So the K-means clustering algorithm is relatively efficient and linear in the number of objects that needs to be clustered. So the big O complexity is NKT, where N, of course, is the number of objects, K is the number of clusters, and T is the number of iterations. And in general, K and T are much small, very small. Usually, for even large data sets, the number of iterations don't go into the dozens. You can converge easily within 10 iterations. And of course, the desired number of clusters would typically be much less than the total number of objects in the data set. So, and we will be discussing other clustering algorithms later on. Most of those clustering algorithms are generally n square in complexity. So this one is n. So that's why this is considered to be linear and efficient. So we said that the K-means algorithm is based on optimization. It optimizes a clustering objective, but the optimization problem is non-convex, so it typically would converge to a local optima or local minima. So if you want to find a clustering that is closer to the global optimum, you will have to run the algorithm multiple times with multiple starting clusters. So that can be both a positive as well as a negative. Positive in the sense that it is not heuristic, it is theory based, and negative that you have a local optima. Then let's some other characteristics. Generally, the K-means only works for objects that are described by numeric attributes. So numeric attributes would allow it to be allow the mean to be computed. So you cannot compute the mean if you don't have numeric attributes. If you have, for example, categorical attributes, you won't be able to compute the mean. So we can use the K-modes as well as the K-Medoids, which we are going to discuss today, if your data set is not based on numeric attributes. So of course, you'll need to specify K upfront, which oftentimes is difficult for any given data set. But there are some techniques to estimate the good K, and we discussed one of them last time. and it's sensitive to noisy data, and this is primarily because it's based on the mean, and the mean is impacted by noise and outliers. So one way to handle this is to remove noise or outliers before running the K-means algorithm. Okay. So these are some of the characteristics and of the K-means algorithm. Of course, we also mentioned that the K-means algorithm is sensitive to the initial selection of the clusters. So, and we also discussed some ways of getting better initial clusters, so which typically would lead to variations of the algorithm. So the K-means algorithm variations usually vary in the selection of the initial K-means. Either they are doing selected randomly or some technique. Let's say the one that we discussed last time, which is used in the K-means plus algorithm. So the similarity between objects, of course, this is dependent on the similarity or dissimilarity function that you're using. And you can calculate the cluster means in batch or incremental form. Uh, of course, generally it is done in batch form, which is what the theory says, but there is a variation that does it in incremental form. So, of course, if you want to handle categorical data, you can discuss K-modes and K-Medoids. So, so let me just wrap up with one more comment. So we said that the cost function for the K-means was defined as this function, sum of over all the objects, and you have the indicator function or the cluster membership function, and then you have the distance x, I, and m, k, where k is the cluster, and rik would be 1 if object I lies in cluster k, otherwise it would be 0. So this is the clustering objective, and we said that d is oftentimes the Euclidean distance. And if it is the Euclidean distance, okay, of course, we can use the Euclidean distance directly as a clustering function. But if you use the Euclidean distance square, x, I, m, k square, then this is, of course, the sum of squared errors. So this is also another objective that is commonly used. And there is really no difference in these two objectives in terms of the optimal solution. But in addition to the Euclidean distance, you can use other similarity or dissimilarity functions as well. So for example, you can use the Manhattan. So you can use the Manhattan distance. You can use in general the Minkowski distance as well instead of the Euclidean distance. So the question would be, when would you be using these other measures? Of course, your application would dictate. Usually, as I said, when you have numeric attributes, Euclidean distance is the most appropriate distance. But if your application dictates that you want grid-based distances, then Manhattan distance would be appropriate. And if your application dictates some other, you can say, variations in the distance, then you can use the Minkowski distance with different value of p. So a p value between 1 and 2, for example, would give you a distance that is between Manhattan and Euclidean distance. And sometimes a p-value of slightly less than 1 is also used. So again, these would be dependent on your application. Of course, if you use Euclidean distance, generally convergence is better. If you use some other measures like Manhattan or Minkowski or some other measure, convergence of the algorithm would become poorer. So, of course, in the purest sense, we will be using the sum of squared error, which is based on the Euclidean distance. Okay, so now let's talk about briefly the K-modes first. So of course, this is a partitional algorithm, very similar to the K-means. The only difference is that cluster representative or POTO is the mode of the objects in it. So obviously the mode is defined for categorical attributes. It can theoretically it's also defined for numeric attributes. So if you think about real valued, interval scale, real scale, interval scale, nominal, and ordinal, so mode is defined for all of them in theory. So, but the K-modes algorithm is most appropriate for when you have categorical attributes. So just to take a quick example, let's say you have two attributes, x1 and x2, and let's say x1 has, let's say you have a data set, you have one, so these are the values. Let me take A and B, let's say A, and let's say B, and let's say A. So the mode would then be defined by the most frequent value of each attribute. So the mode would be what? In this case, for attribute A, you have A, x1 you have A, and for attribute B, so also B is also A. So the most frequently occurring value of each attribute forms the mode. So this now becomes the representative of the cluster. And then since we are dealing with categorical attributes, you will also be using an appropriate similarity or dissimilarity function, for example, the Jacob coefficient, to find the similarity between an object and its mode. Okay? So of course, the mode and the data set is discrete. So this algorithm tends to be unstable. K mode can be unstable in convergence. But of course, the positive is that it is applicable to categorical attribute data sets, while the K-means is not. Okay. So generally, this K-modes, although we won't go into detail, is generally related to item set mining. So remember we discussed item set mining previously where we found frequent item sets. So K-modes also is what? For each attribute, we are finding the most frequent value. And if you have multiple attributes, we are finding the combination that is most frequent. So variations of this idea is also used in the item set mining. So in the literature, you will see parallel between K-mode based clustering and item set mining based clustering. Okay, so there are clustering algorithms that use the idea of item set mining. So we won't go into the details of those, but the point I want to mention here is these algorithms are applicable to categorical attributes. So now let's look at the K-Medoids. So the K-Medoids algorithm, again, is a partitional algorithm. And as the name suggests, it represents, so cluster is represented by the, you can say, median object. So that's where the name Medoid comes from. Or in other words, the centrally located object. So in K-means, the cluster representative or prototype was the mean of all the objects in the cluster. And the mean may not be an actual point. The mean may not be an actual object. It would be just a point in space. And similarly for K modes, we are taking the mode, and that may not be an actual object. It would be a point in space. While in K Medoids, the representative or the prototype is an actual object. What is the characteristic of that object? It is the centrally located object. Okay. So the median or mode, so the median can be calculated, of course, for ordinal and higher attribute types. So ordinal, interval scaled, and ratio scaled. Of course, the median cannot be computed for nominal attribute types. So the K-Medoids thus can be applied to attributes that are ordinal, interval scaled, ratio scaled. So numeric attributes as well as ordinal categorical attributes. And secondly, it is based on the median, which is a more robust representation of the cluster. So it's less prone to noise and outliers. Okay? As opposed to, for example, the K-means algorithm, which is quite sensitive to outliers. All right. So now let's discuss how this. So the question obviously is, how do you find the Medoid? Of course, the algorithm overall structure is the same as K-means. You basically start with initial objects as Medoids, and then you have the iteration which is iteration of the algorithms. And then for each object, you try to assign it to the nearest Medoid using whatever similarity measure that you are using. Once you have the assignment, you will then need to recompute the Medoid. So that's where the difference arises. So the question is, how do we determine the Medoid? So mean, of course, is very easy to determine. You take all the objects and take the average. Mode is also easy for each attribute and for all the objects in a cluster, take the maximum, the most frequently occurring value, and so on. What about the middle object? How do you find that? So in general, what is a median? If you have a 1D data set, the median is a centrally located data set. But if you have, in general, a ND data set, how would you find the centrally located data set, centrally located object? So let's say if you have some points, maybe in 1D, 3, 6, 9, 10, 11, okay? So 9 is the middle object, okay? This is 1D. So this was easy because we were able to rank the objects. But if you have n-dimensional objects, how would you be able to rank it? Or in other words, how would you be able to find this object 9? So the idea is actually quite easy. This object 9 is the object that has the least distance, you can say sum of distance from all other objects in this data set. So let's say if you had taken 3 as the medoid, the distance of other objects from 3 would be what? 6. 6 minus 3, 9 minus 3, 10 minus 3, 11 minus 3. So this would be a larger number as compared to if you take 9 as the middle object, the distance of all other objects from 9 would be the smallest. So 6 minus 9, 3 minus 9, 10 minus 9, 11 minus 9, this sum would be the smallest. So this is the idea that we will use to find the middle object. So there's no other way of finding the middle object if your objects are n-dimensional. So let's then look at the algorithm in a bit more detail. So specifically, there are many variants of the K-Medoids algorithm. There's one particular variant called partition around Medoids. Partition around Medoids. Okay. So the algorithm proceeds, of course, for the most part, similar to the K-means. So let's say now you have assigned objects to their respective Medoid, the current Medoids. Now you want to find the new Medoid. So at any given point in time, you'll have K Medoids, right? And then at any given point in time, you'll have n minus k non-Medoids, right? K is the number of clusters, okay? So to find a new Medoid for any given cluster, let's say we are talking about cluster, let's say small k, okay? So cluster small k, currently it has, let's say, object, let me say object 3 as the Medoid, okay? Is current Medoid. So what we do is we replace x3 with every other object, which is not actually a Medoid already, okay? So if you replace x3 with the other object, there is some repercussion. So you'll get a reassignment, meaning that you have removed x3 as the Medoid. So you will have to do a reassignment again. And after that reassignment, you have a cost. And cost, of course, is the sum of the distances of all objects with their respective Medoids. If that cost, so let me say in this way, so x3 मैंने replace कर लिया with, let's say, so let me just take a hypothetical example, n is equal to, let's say, 5, ठीक है? And let's say k is equal to 2, ठीक है? So x3 is the current Medoid for cluster 1, and let's say x5 is the current Medoid for cluster 2, ठीक है? So what do we do? Let's say we are talking about cluster 1. So current Medoid x3 है, ठीक है? So what we'll do is we switch it with x1. So in other words, आप कहेंगे try x1. So when you switch it with x1, the reassignment would occur for the entire clustering. Reassignment होगी. So in other words, let's say ये आपका initial cost is C. Sum of the so this was the cost for when you use x3. So after trying x1, you get a cost using x1. ठीक है? So if the cost of x1 is less than the cost of x3, then this is a candidate replacement for x3. ठीक है? Why candidate? Because we still have to try the others. So ये x1 try किया था. Now we try x2. ठीक है? So we'll get cx2. और इसको भी आपने कर लेना है. And then we try, what do we, x3 तो करेंगे नहीं, of course, x4 हम फिर करेंगे x4, right? और आपके पास c x4 आ जाएगा. ठीक है? So let's say all of them are less than cx3. So you will choose that object which is the least cost, जिससे सबसे थोड़ा cost आ रही है, which basically says that now this is the middle object. Distances from all the other points has reduced. So select the object that has minimum cost among c x1, c x2 भी था और c x4. ठीक है? So now this would be the new Medoid for cluster 1. And of course you do this for cluster 2 as well, which is x5. तो x5 की options आप देखेंगे x1, x2, x4 and so on. ठीक है? So now you have new Medoids, then you repeat, you assign again. बाकी algorithm का flow वही है जो K-means वाला है. Only the difference is the finding of the Medoid, because this is not like the mean that you can do it in a simple calculation. You have to find it through an iterative process. So is this point clear? So the K-Medoids is based on the middle or central object. It's less prone to outliers. So that is a big advantage of the K-Medoids. And secondly, it is applicable to non-numeric attributes dataset as well. So K-Medoids is also reasonably popular in practice in addition to the K-means algorithm. Okay, the computational complexity. Of course, time complexity. So इसकी time complexity क्या है? So of course, बाकी तो framework वही है, KT वही है. So आपके पास एक big outer loop है, number of iterations, और within each loop आपने हर cluster पे जाना है. But हर cluster के अंदर फिर आपने reassignment भी करनी है. ठीक है? So if you talk about one reassignment, what did we do? We had n minus k objects, and we checked with k Medoids. So for example, K-Medoids तो आ गया, but उन K-Medoids के साथ आपने n जो आपके पास ऑब्जेक्ट्स हैं वो स्वैप करने या चेक करने. सो इन अदर वर्ड्स, दो दफा आप n पे घूमेंगे. एक दफा n आपकी असाइनमेंट हो रही है, दूसरी दफा n आप करेंगे टू फाइंड द मेडॉइड. ऑफ कोर्स दूसरी दफा n माइनस k होगा, नॉट फुल n, बट बिग O की जब हम बात करें और k छोटा है तो you get, you would say n square. ठीक है? Of course, if you want to be pure, n into n minus k. ठीक है? So the computational complexity is the square in n number of objects. We go over each object for assignment, and we also go over each object for the finding of the Medoid. So as such, it is less computationally efficient as compared to the k-means. And kind of this is normal for clustering. N square is normal for most clustering algorithms. Really, you can't do any better than that unless you have some kind of distance-based data structure in which this may become n log n. कोई आपने KD tree बनाया हुआ है data set के ऊपर. Of course, I don't know if you guys study KD trees in data structures, which are distance trees, distance-based indexing of objects. So if you do that, then this would be reduced to that level. But as I said, n square हो जाता है in general. Okay. So that was the K-Medoids. So we have discussed K-means, K-modes, and the K-Medoids. And K-modes and, K-means and the K-Medoids are relatively popular in practice. There are some other variants of partitional algorithms and of these approaches. Some of them are based on sampling. So we will not discuss these in detail, but there are some names like Clarence, for example. ठीक है, Clarence. So sampling base, of course, would be so of course there is some sampling error as well. So obviously it will be an approximate algorithm or approximate solution. And secondly, of course, it can be used for large data sets. You can sample those data sets and do the clustering. So I think with that, let's conclude partitional algorithms and move on to hierarchical algorithms. So let's move on to hierarchical. So as we mentioned earlier on, primarily there are two big categories of clustering algorithms. One is partitional clustering algorithms. The second is hierarchical clustering algorithms. There may be other categorizations as well, but these are the two big ones or the more common ones. So hierarchical clustering, as the name suggests, is it builds clusters iteratively. Of course, K-means and partition also does it iteratively, but here I'm saying it builds clusters iteratively in the sense that either it is agglomerative, which means that initially all objects are independent clusters, and then iteratively you do merge clusters. So at each step you merge the most similar cluster to reach to the next step, and then you continue. So in other words, as you can see, initially the number of clusters is n, then it would go down to n minus 1, and then maybe n minus 2, until you get just one cluster, which of course is useless, but I'm just saying this is the process. You start with each object being its own cluster. In other words, k is equal to n, and then you do merge. Maybe you merge 2 points, 2 objects, and you now get n minus 1 clusters. One is a bigger cluster with 2 objects. And you continue hierarchically in this fashion. until, of course, if you do it, continue it, you'll merge all the objects into one big group, which of course is useless. But this shows you the process. Okay? Of course, you can do this in the reverse way as well, which is called divisive. Okay? Reverse of agglomerative. So start with one cluster, then partition. Partition / split iteratively. So both directions of hierarchy are possible, but of course, both of them are similar, of course. But in practice, mostly we use the agglomerative process where we merge objects. Okay? So let's take a very simple example, 1D again. So 1D example to illustrate this. So let's say we have some points like, of course, 1D example cross are ज़्यादा easy होता है, but still just to illustrate. So we have, let's say 10, 11, 15, 20, 22, 25. ठीक है? Okay, so let's say we have these 1D objects. Initially, each of these objects is its own cluster. So 5, 10 is a cluster, 11 is a cluster, 15 is a cluster, 20 is a cluster, 22 is a cluster, and of course 25 is a cluster. So we have as many clusters as objects. So then after that, we merge the two clusters, in this case now just objects, which are the most similar. So if you look at this, so which two objects have this least dissimilarity? So 10 and 11, right? So 10 and 11 would merge. And then of course we have 15, we have 20, and we have 22 and 25. So तो ये parenthesis डालने का मतलब ये है कि ये cluster है. So now we have one less cluster, and 10 and 11 are grouped into one. Okay? So now we repeat the process. Okay? So now we find the two clusters that are most similar. So now in hierarchical clustering, we need to have a measure that can quantify the similarity between two clusters. So previously we had talked about similarity measures or dissimilarity functions between points or objects. So now we'll need to extend that to clusters as well. For 1D, it's quite easy. So let me continue this process. So which two clusters are most similar? So 10 and 11 is one cluster. Then we have 15. 15 is, so how would you find the distance of 15 with the cluster 10 and 11? So there could be various ways. So one way could be you find the average of 10 and 11, mean of 10 and 11 and compare it with 15. One way could be you just find a minimum distance between 10 and 11 and 15, which would be 15 and 11, which is 4. Another way would be the maximum distance between 15 and the cluster 10 and 11, which would be 5, 15 and 10. Okay? So let's say I use the notion of minimum distance. So 15 and 11 is 4. So 15 and 20 is 5. And then, of course, 22 and 20 is 2. Okay? And 22 and 25 is 3. So most similar फिर कौन सा हुआ 20 and 22. So now the next level would be 10, 11, so 15, then 20 and 22 gets together. And then of course 25. ठीक है? So now we repeat the process again now. We find the two clusters that are most similar. And if I use the minimum distance between two clusters, so between 10 and 11 and 15 का distance 4 है, 15 का 20 और 22 का distance 5 है, 25 का 20 और 22 से distance 3 है. तो minimum वो वाला हो गया. तो we go one up, 10, 11, then we have 15, then we have 20, 22, and 25. So now you notice that we have 3 clusters. Okay? And then if you go one level up again, so 10, 11, and 15 gets here. And then we have 20, 22, and 25, 2 clusters. And of course, if you go up one more level, it's just one cluster, which is of course a trivial cluster. So you notice that I built the tree from bottom up. So there's a root up there, which is one cluster, and then we have divisions. So this structure, you can call it a hierarchy of clusters. In the hierarchical clustering literature, we also call this structure a dendrogram. Of course, dendrogram has lines that show the relationship between clusters. So let me show you with an example maybe. So the dendrogram, as I said, is a structure. So let's say we talked about the example, we have 10 as one, and we have 11 as the other. And these were merged at the first level. So these are represented by these lines like this. So you have lines that go up, and when they merge, you join those lines. So 10, 11 join हो जाएगा, और आगे let's say हमारे पास जो 15 था वो नहीं हो रहा था cluster में, वो separate एक line आएगी, उसकी line नहीं होगी. If there are 2 points that are combined, they will join. And so at this level, you will have all of these points separately. So ऊपर जाके, for example, आगे ऊपर जाके, let's say काफी ऊपर जाके, we had something like, ये let's say मैं फिर लिखता हूँ उसको, ये यहाँ 10 था, और यहाँ 11 था, और फिर यहाँ 15 था. 15 बहुत ऊपर यहाँ चले गया, और ये यहाँ आके मर्ज हो गया, तो ऊपर जाके ये दोनों मर्ज हो रहे हैं. ठीक है? So in this way, you can find out which objects are merged at a given level. So this dendrogram has levels. Each level is obtained after one merger. So of course, the complete dendrogram would be, I'm just going to draw it randomly. Complete dendrogram, let's say कोई ये आपके पास है, ये ऊपर जा रहा है, यूं इधर है, ऊपर ये जा रहा है, ये दो यहाँ मर्ज हो रहे हैं, ऊपर निकल रहे हैं, तो फाइनली मर्ज हो रहा है. So you can have dendrogram drawn like this. That shows which objects merge at which level. ठीक है? So this was the dendrogram structure that you can draw after you have done hierarchical clustering. Okay, now coming to the cluster similarity. So remember we said that if you want to merge two clusters, you will need to determine the similarity between two clusters. So previously we had only discussed similarity between objects. So let's say if you have cluster 1, let's say C1 or Ci, and cluster 2. So what is the similarity between them, or dissimilarity between C1 and C2? So this is what we want to quantify. So there are various techniques, and we discussed those techniques while we did the example, but they have some special names, so let's discuss those. So one is called the single link distance or similarity. So single link, of course, these names, the first two names, of course, are not very intuitive. So single link is the minimum distance between the two clusters. So single link D, C1, C2 is the minimum distance between objects in C1 and C2. So you can think of one link connecting those two objects. So in the example above, for example, 10, 11, or 15, 15 or 11 is the minimum link or the single link, because this is the minimum distance, the most similar distance. Okay. So then we have what is known as the complete link. So complete link, again, as I said, these names are not very intuitive. So D, C1, and C2 is basically the maximum distance between objects in C1 and C2. So again, if you think in terms of graph, this is still one link. It's not a complete link, it's still one link, but this link is the link that has a maximum distance. So in the case of 10, 11, and 15, this would be the distance between 15 and 10. Okay? So complete link can also be used, single link can be used. And then we have the centroidal distance or centroidal link. So of course, this is intuitive, C1, C2. So basically the distance between centroids of C1 and C2. A centroid could be defined in terms of mean, mode, Medoid, whatever is appropriate for you or appropriate for the data set. Okay? And then finally, we have also an average link or distance, which of course, as the name suggests, is the average distance between points in the two objects. Average pairwise ठीक है. So these are the most common 4 techniques for quantifying distance or similarity between two clusters. The common techniques that are used are single link and the centroidal link. The single link is the minimum distance, which is based on the, you can say, a link between the 2 points in the 2 clusters that are closest. And the centroidal would be, of course, based on their center, which can be defined by the mean. So for example, if you have a cluster 10, 15, and let's say 22, and you have another cluster, let's say 25, 26, and 27. So the single link would be what? So single link would be 3, right? So complete link would be, of course, this is 1D. If you are using multi-dimensional and we have multi-dimensional data set, then of course you will be using whatever appropriate similarity function that you have to find the 2 points which are most similar. तो ये 1D था तो हम सिंपल ये निकाल लेते हैं. So the so complete link would be 17, and then of course average link or centroidal link उसी तरह ही आप निकलाएगा. If you take the mean of the first and the mean of the second, mean of the second I think is 26. तो पहले का अराउंड 16 होगा मेरे ख्याल से. 10, 15 and 22 का मीन क्या है? So for example, 10 plus 15 plus 22 divided by 3.
15.6.
जी. So 115.6, ठीक है ना? So of course then if you were taking the centroidal link, this would be of course 26 minus 15.67. Okay? But whatever measure that you use for a particular clustering, you use it consistently. ये नहीं है कि आपने एक iteration पे single link लगाया, दूसरे iteration में complete लगाया, तीसरे पे आपने centroidal लगा दिया, and so on. You stick with one throughout your clustering. So if you use single link, then if you use single link throughout. ठीक है? Okay, so that was the the hierarchical clustering. So let's quickly look over some of its properties. So first of all, computational complexity. So what happens? So you have how many iterations in the worst case would you have? Iteration is the height of the tree. So if you merge just one object at each iteration, so the height of the tree would be n, right? Because एक object काम कर रहे हैं आप at any given point in time. And of course, आपने n object काम करने तो n height होगी. Of course, that is trivial. You would of course go to n. You will stop somewhere in between. But I'm just saying in the worst case, you might go up to n. So now that's the number of iterations. Now what about within each iteration? Within each iteration, what do? You are looking at one object and comparing with every other object to find which one is most closest. So हर एक object and every other object. So that's n square. ठीक है? So of course n square is the time complexity at each iteration. And you can say you have k iterations, which is the height of the tree. ठीक है? Of course, k in the worst case would be equal to n in the worst case. ठीक है? तो in the worst case, of course, अपने पूरा ही ट्री बनाना है तो n क्यूब कॉम्प्लेक्सिटी है इसकी. ठीक है, बट ऑफ कोर्स पूरा ट्री बनाने के तुक नहीं बनती, तो आप कहीं बीच में रुक जाएंगे. सो विच केस इट विल बी n स्क्वायर इनटू k. सो नाउ द क्वेश्चन इज के हम कहाँ रुकेंगे. सो रिमेंबर, hierarchical clustering do not take k as an input as opposed to partitional clustering algorithm. So k is not an input. So we let the algorithm do merging, and you can stop at whatever k that you feel like is most appropriate. So generally, so what is the stopping criteria? So actually the stopping criteria is usually evaluation based, and we haven't studied evaluation so far in clustering. So meaning that के आपकी जो भी clustering उस level पे आ गई, you determine the quality of that clustering. If the quality is good, then you stop. So evaluation based can be both quantitative as well as qualitative, meaning that humans can look at it and decide whether this is the best clustering. So actually this hierarchical clustering is often preferred for iterative clustering by humans, iterative and interactive clustering. Okay? So you start with all objects as cluster, and then you iteratively merge clusters, form bigger clusters, and you stop when you feel that you have found the ideal number of clusters. And of course, based on some evaluation, which might be based on quantitative numbers or even qualitative judgment. ठीक है? All right. So, and also it's often, you can say, used as a pre-clustering before applying another technique. Most likely the K-means technique. So what does this mean? So in other words, you use your hierarchical clustering algorithm, do some merging, some clusters. Not, let's say, your ultimate, let's say you have 10,000 objects and you want 10 clusters. You start with hierarchical clustering, and maybe you have found 300 clusters. And then now you send those 300 clusters with their initial centroids to the K-means algorithm and do the further clustering. So in other words, hierarchical clustering can help you find initial clusters that will improve the performance of subsequent clustering algorithms like K-means. ठीक है? Okay, so these were two things. Another point that we need to consider is hierarchical clustering in general does not have a global clustering criterion. So for example, if you compare it with the K-means, it is not optimization based. So you can say that it's maybe local optimization, but not global optimization. Okay? So one other consequence of this is that there is no iterative relocation possible. So what does this mean? So for example, if you have merged 10 and 11, 10 and 11 will always remain together as you continue your clustering. So only new objects would be added to this cluster. They will never be removed from this cluster. So objects are never removed once they are added to a cluster. So maybe, let's say you have made a wrong merge decision. Once that wrong merge decision has been done, it will be propagated throughout your clustering algorithm. So this is not the case for k-means, which use a global clustering criterion. They can relocate objects as the clustering iterations proceed. While in hierarchical clustering, this is not possible. So from a algorithmic perspective, from a theoretical perspective, this is a major difference between k-means and hierarchical clustering. Okay? So we're also running out of time. I'm still at 10 minutes. Okay. So I think more or less we have covered most of the characteristics of the general hierarchical clustering algorithms. So next, I will discuss a special case of uh, hierarchical clustering algorithm, which is kind of incremental. And the algorithm has a name called Birch, which is clustering with hierarchies using trees. So, of course, this is hierarchical clustering in the purest sense, but as I said before, hierarchical clustering can often be used as a pre-clustering before you apply some other partitional clustering algorithm like k-means. So same is true for Birch. You can use Birch for pre-clustering before applying k-means. So, but while applying Birch, this is the main characteristic of this is incremental clustering. So all data objects need not be available at start. Okay? In the other algorithm that we saw, all data objects need to be present or available at start because we need to find the pairwise similarity or dissimilarity between them. In this Birch, we don't need that. And as such, it does incremental clustering. Maybe you're clustering a stream of data objects. Objects are arriving one after the other, and then you're clustering them as they arrive. Okay? And Birch, the original Birch, of course, is only applicable to numeric attribute data sets. Of course, hierarchical clustering can be applied to any types of attributes because it only depends on the similarity function. If you have a similarity function defined between objects and between clusters, then you can apply hierarchical clustering. It can even be mixed attribute types. Yeah. So the Birch algorithm uses the idea of clustering features. And using this clustering feature, it creates a data structure like a hierarchy, which it calls the clustering feature tree. So in other words, CF and CF tree. Okay. So what is a CF? I think we are running out of time. I'll do this and then end it. CF is a clustering feature, is a vector that summarizes key stats of a cluster. And from these stats, or from these, you can say stats, you can obtain some important further stats that are relevant for clustering. So in general, clustering feature for a given cluster consists of three things. One is n, which is the number of objects in the cluster. The other is the linear sum, which is the linear sum of the objects feature in the cluster. And then we have the squared sum. So let me just take a simple example. Let me take a 2D example. Let's say cluster आपका दो clusters हैं. एक ही cluster की बात हो रही है. Let's say we are talking about one cluster and it is 2D. So 1, 3 एक object है. और let's say 2, 3 दूसरा object है. So what does this mean? So two objects n is equal to 2, right? LS is the linear sum. So we take the sum of each feature of all the objects in the cluster. So in this case, we have 1, 3 and 2, 3. पहला feature 1 और 2 है. तो दोनों का sum करेंगे तो पहले का 3 हो जाएगा, दूसरे का 3 plus 3 6 हो जाएगा. This is the linear sum. And the squared sum, अब दोनों को square करके sum करेंगे हम. So for example, 1 square plus 2 square, which is 4 plus 1, 5. And 3 squared is 9 plus 3 squared 9, which is 18. 9 plus 9, 18. So इसका फिर CF क्या होगा? 2 क्या था? 3, 6, and then we have 5, 18. So this is the CF for this cluster. So what is the advantage of this CF? You know the number of objects, and given the linear sum or the squared sum, you can also find the mean of this number of points. You can also find some other parameters like the diameter of this cluster. And I think we will discuss this next time. And then you can do operations on this CF rather than the entire set of objects. So any questions?
There aren't any students in the class, so I think we can end the session.
जी फिर से बोले.
क्लास में कोई स्टूडेंट नहीं है, सिर्फ मैं ही हूँ.
मैं देख रहा हूँ 2 ही हैं, आप ही हैं, शहजाद हैं.
सर तो सेशन
क्लास
एंड
में
कर
बीच में भी कोई था?
नहीं सर, सिर्फ मैं ही था.